Welcome to Lecture 4 in our course, Analysis of a Complex Kind. Today we'll talk about roots of complex numbers. You all know that the square root of 9 is 3, or the square root of 4 is 2, or the cube root of 27 is 3. But how would you take the square root of 3 plus 4i, for example, or the fifth root of negative I? That's what we're going to talk about today. Let's begin with a definition. Suppose w is a complex number. Then we say an nth root of w is another complex number z, such that z to the n is equal to w. So we'll see that if the number w is a root we're taking is not equal to 0, then there are exactly n distinct nth roots. So there are 2 distinct square roots of any number, there are 3 distinct cube roots, and so forth. And how do we see that? We use the polar form for w and z to show this. So we'll write w as rho e to the I phi, and z as r e to the I theta. So you notice we just introduced yet another Greek symbol, namely the symbol rho here for the radius, because r is already used up for the radius of z. Now, if we use these notations, then z to the n equals w, that equation, that defining equation for being an nth root, that equation becomes, if we write instead of z, r e to the I theta, then we get r to the n, e to the I n theta, by the rules of how to manipulate this e to the I theta, is equal to w, which is rho e to the I phi. So if you compare these two complex numbers in polar notation, one or two numbers the same, they're the same if they have the same distance from the origin, and their angles agree modulo 2 pi. So r to the n has to be equal to rho, and this angle, n theta, has to be talking about the same angle that phi is talking about. So in other words, they can differ by 2 pi over 4 pi, but they can't differ much other than that. So n theta is pretty much the same as phi, except maybe for a 2k pi. So r to the n is equal to rho. That means r itself is the nth root of rho. And since rho is just a positive real number, by nth root, when I write the symbol nth root, I mean the regular nth root that we all know. The regular nth root, not a complex root, it's the regular nth root of rho. And n theta has to be equal to phi plus 2k pi, where k is some integer. So I can divide this equation by n, and I get theta has to be phi over n plus 2k pi over n. And it turns out, if I look at the values of k for 0, 1, and so forth, up to n minus 1, I have exhausted all possibilities. After that, things start repeating. So these are actually distinct roots. And if I look at k equals n, for example, when k is equal to n, what would I get? I would get theta is equal to phi over n plus 2, and now when k is equal to n, 2n pi divided by n, and that n would cancel out, so I would have phi over n plus 2 pi. But I already looked at the angle theta equals phi over n when k was equal to 0. So I would get kind of the same angle as the one I got when k was equal to 0. And so I don't get any new angle. I'm getting different angles here for k equals 0 through n minus 1, and then the angles start repeating. And so I get all my different solutions as w to the 1 over n, this is how I denote my solutions, is equal to the nth root of rho times e to the I phi over n plus 2k pi over n, where k runs through the value 0, 1, all the way to n minus 1. So these are the nth roots of the complex number w, and they're all distinct from each other. And the best way to really understand this is to do a bunch of examples, and that's what we're about to do. So here again, I wrote down this formula we just found. If w is of the form rho e to the I phi, then the nth roots of w can be found with this formula for these n values of k. So let's find the square roots of 4i as an example. So first of all, 4i, we need to bring that into this form, in the form rho e to the I phi. So we have to figure out what's rho, what's phi. Well, 4i is 4 times, and instead of I, we can write e to the I pi over 2. We discovered that during the last lecture. And so in other words, this rho is 4, and phi, and a possibility for the angle is phi is pi over 2. And we want to take the square roots of the second root, so n is 2. So now we have everything we need to plug into this formula. So we find 4i to the 1/2 is equal to the square root of 4 times e to the I. Now we need to take phi and divide it by n. Phi is pi over 2 divided by n. That gives me pi over 4. Plus 2k pi over n. We'll just write that down. 2k pi over 2 because my n is 2. So here's the complete formula, and we need to plug in k equals 0, and then k equals 1. So we get 2 separate solutions. For k is equal to 0, this whole second term, 2k pi over 2, is just not there, and so we find square root of 4, which is 2 times e to the I pi over 4. That's one of my 2 square roots. And when k is equal to 1, 2k pi over 2 becomes 2 pi over 2, which is pi. So I get 2 times e to the I pi over 4 plus pi. But remember what e to the I pi equals? Pi is a 180-degree angle. E to the I pi is this number right here that forms a 180-degree angle. That's the number minus 1. So since I can pull this exponent apart, e to the I pi over 4 plus pi is actually the same as minus e to the I pi over 4. So the second solution is the same as the first solution except for a negative sign. So these two are actually the same except a negative, so plus or minus. And remember what e to the I pi over 4 was? We also looked at that during the last lecture. E to the I pi over 4 was this number on the unit circle at a 45-degree angle, and we found that was root 2 over 2 plus I times root 2 over 2. If I multiply that number by 2, it becomes root 2 plus I root 2. So root 2 plus I root 2, I see that right here, and with a plus or minus, plus for the k equals 0 solution, minus for the k equals 1 solution. So in a picture, I'm drawing a lot of pictures here all over the place, the square roots of 4i, where are they? 4i is kind of far up on the y-axis. I is here. The square roots of 4i are at distance 2, so on the circle of radius 2, and at a 45-degree angle. That's one of the square roots, and the other one is over here. So these are the 2 square roots of 4i. And in coordinates, they are plus or minus root 2 plus I root 2. Let's do the same thing for the cubed roots of minus 8. First step again, we have to write minus 8 in polar form. Well, it's not just minus 8, because the polar form has to have a positive radius right here. Well, the radius of minus 8, the norm of minus 8 is 8. And the minus sign, we get that by writing e to the I pi. So 8 times e to the I pi, that's the polar form of minus 8. So in other words, this rho is equal to 8. And phi, the angle, is pi. And we want to take the cubed roots. So my n is 3. Again, now I have everything I need to plug into this equation, and I can go ahead and do that. So the cubed roots of 8 can be found by taking the regular cubed root of 8. This is just one cubed root of 8, the one 8 being a positive number, so that's actually 2. So this number right here, that's simply 2, because 2 cubed is 8. Times e to the I, phi over n. Phi is pi, n is 3, so I get a pi over 3 right there, plus 2k pi over n, so 2k pi over 3. And now I need to consider k equals 0, 1, and 2, because I'm taking the cubed roots. So let's start with k equals 0. So this whole second term isn't there when k is equal to 0, and I simply get 2 times e to the I pi over 3. When k is equal to 1, the second term becomes 2 pi over 3. So I have pi over 3 plus 2 pi over 3. Well, that's 3 pi over 3, or simply pi. So for k equals 1, my root becomes 2 times e to the I pi. But remember, e to the I pi is negative 1. So the second solution is negative 2. And indeed, if you check that, negative 2 cubed, what's negative 2 cubed? Well, negative 2 cubed is negative 8, indeed. And the third solution is 2 times e to the I pi over 3, and now we have to plug in k equals 2, so 4 pi over 3. But pi over 3 plus 4 pi over 3, that's 5 pi over 3. So this is the third solution we find. Let's try to draw a picture where we find where these solutions are. So minus 8 is somewhere way down here on the negative x-axis, and we want to find the cubed roots of 8. So they're all on the circle of radius 2. So here's 4 and there's 2. So here's the circle of radius 2. All cubed roots have radius 2. And one of them is at angle pi over 3. One of them is at angle pi, and one of them is at angle 5 pi over 3. So here's the angle pi, and there is pi over 3, and there is 5 pi over 3. So these are the cubed roots of negative 8. Just a quick other definition. The nth roots of the number 1, those are called the nth roots of unity, because 1 is kind of a unity. So what do those look like? Well, the number 1 is, in polar form, 1 times e to the I times 0, so the angle is 0. So if we plug that into our formula, we get the nth roots of 1 is the regular nth root of 1, which is, well, just 1, times e to the I, phi over n, phi is 0, so 0 over n, plus 2k pi over n. And k runs from 0 through n minus 1. So replacing the nth root of 1 here, so for the number 1, I get e to the I 2k pi over n. So these are the nth roots of unity. And again, let's draw a picture to understand what they are. So this time, 1, I'm going to draw that right here. And let me draw the circle of radius 1 right here. So this is the circle of radius 1, and I want to find the nth roots of 1. And they're all of radius 1, and their angles are 2 pi k over n. So for example, for the 8th roots of 1, I need to find the angle 2 pi over 8. This is 2 pi over 2, because that's pi 2 pi over 4, so 2 pi over 8 will be here. 2 times 2 pi over 8, 3 times 2 pi over 8, 4 times 2 pi over 8, 5 times 2 pi over 8, 6 times 2 pi over 8, 7 times 2 pi over 8, and this is 0 times 2 pi over 8. So I have these equally spaced points on the unit circle that correspond to the 8th roots of unity. I simply divide the whole angle into as many parts as necessary, and that gives me the nth roots of unity.